Good afternoon. Good afternoon.
Good afternoon, sir.
Good afternoon, sir.
Shall we start the second module?
Yes, sir.
Okay. I'll give the basics of this chapter first, and we can go ahead with the derivation and other things later on. Module 2, analysis of stress and strain. What is analysis of stress and strain? We will discuss. Now, let us consider a body like this. Body is three-dimensional like this. It is fixed like this. It can be fixed like this. It can be subjected to load P1, P2. There can be a UDL like this. Let's say P, this is in this direction. Okay, P Newton per meter. P Newton per meter. There can be body for other things. We will not consider all this. We'll say that the body is subjected to forces. Now, until now, what we have discussed is, for example, if I consider a bar like this, one of the side is fixed, other side it is subjected to load P like this. If I take a section like this, if I take a section, this is P. If I say this is the resultant force, I can write sigma is equal to P by A. This is one dimensional. Stress is in only one dimension. Either instead of this, there can be resultant force. There can be forces acting like this. I will take the resultant of all this force per unit area of cross section gives us stress in 1D. But generally, when I talk about a three-dimensional body like this, a three-dimensional body like this, or an irregular body, okay, three-dimensional body. In this case, this is a 1D body. Stress is in one direction. Stress is in one direction, one dimension, along the length. Along the length. When I consider a three-dimensional body, what you have to know is there are, I will not go in depth of this, but you should know that. But there are 6 stress components. Generally, I can write 9 stress components. Sorry, 9 stress components. Others are complementary. We will discuss later. 9 stress components. I will discuss this. Sigma x, tau xy, tau xz, sigma y, tau yx, tau z, tau zx, tau zy, sigma z. Okay. See, there are 9 stress components which are required to. If I know the 9 stress component, I can solve. Any problem at a given point. What you have to know is, for example, if I consider a plane like this. If I consider a plane line like this, there are infinite number of points. There are infinite number of points. And if I consider this point, I can pass infinite number of planes. I can pass in, this is x, this is y, this is x dash, this is y dash. infinite number of planes. But what you have to know is, if I know only this 9 stress components, sigma x, tau xy, tau xz, tau yx, sigma y, tau yz, like that, if I know this 9 stress components, I can find the stress on any other plane at that point. Okay, stress varies from point to point and plane to plane. If we know if we know 9 stress components on three mutually these are on three mutual perpendicular planes, by transformation we can find the state of stress on any other plane at that point. So if I say a body has infinite number of points, and at each point I can pass infinite number of planes, and at each plane the state of stress is different. But if I know the state of stress on only three mutual perpendicular planes like this, the x, y, and z planes, I can find the stress on any other plane at that point by transformation. Transformation in the sense, if I know, for example, I want to stress on this plane, this is x dash, y dash, and say z dash. I want this plane. This is at an angle theta with respect to x. So by transformation, by representing, for example, sigma x is equal to sigma x dash cos square theta plus sigma y dash, sigma x dash is equal to sigma x cos square theta plus sigma y sin square theta, something like that, or sigma y dash is equal to sigma x sin square theta plus sigma x cos square theta, something we will derive that. But time being, you know the transformation in the sense, by changing one plane to another, by changing how do we obtain the stress on another plane, and that by using transformation. If I know the state of stress on one plane, by using analytical relation I can find the stress on another plane. How do you obtain that? I will represent the state of stress. Anyhow, I know the state of stress on this plane. For example, if I take a cube, let's represent, this is state of stress. This is very important. See how I will write. First, I will write the normal components. This is explain sigma x, sigma x. This is sigma x. This is sigma y. This is sigma y. This is sigma z. This is sigma z. What you have to know is, if I write tau xy, always a plane is determined by its normal. This is the normal to the plane. For example, if I call you, your name might be confusing. There can be Arvind A, Arvind G, Arvind S, or Arvind A only twice. Two per names can be Arvind A. For that, if there is a USN, that's why the university gives the USN. This USN is remains the same throughout. It's completely same for anywhere you go. Your USN remains the same. For your even somewhere for gate and all, they will ask the USN. The USN remains the same. For that USN, that remains, that is an identity for you. So for a plane, the identity is normal. This is the normal. I can call it as normal. This is the normal. So for this plane, normal is along the x direction. For this plane, normal is along the y direction. For this plane, normal is along the x direction, y direction, and z direction. Normal in the sense perpendicular to the plane. Normal in the sense normal. There is no special meaning. Perpendicular line perpendicular to the plane. A line perpendicular to the plane. Okay, tau xy means the first letter indicates normal to the plane. Tau xy in the sense normal to the plane is in x direction. This is the normal to the plane. Okay, normal to the plane, normal to the plane is x, not x direction. Normal to the plane is x. Normal is to the this plane. Normal to the plane is in x direction. Y indicates stress is acting in y direction. If I write tau xy will be like this. Tau xy normal to this plane is in x direction and the stress is acting in y direction. If I write, meanwhile, as soon as you write tau xy in the opposite sense, you should write normal to the plane. This is also x space. You should write tau xy. Now, normal to the plane is in x direction. The plane remains the same. Normal to the plane is in x direction. Stress is acting in positive direction. Opposite to that should indicate tau x head. Okay, don't worry, this is for your information I'm writing. Next, this is the y plane. Normal to the plane is in y direction and normal to the plane is in y direction. Stress is acting in x direction. You should write like this. Normal to the plane is in y direction and the stress is acting in z direction. Normal to the plane is y direction, stress is acting in z direction. This is the positive z. If I write, this is y, this is x, this is positive z. I should write tau yz. Next, for this sigma z, normal to the plane is in normal to the plane normal to the plane is in z direction and the stress is acting in x direction. In this, on the other side, you should write in the opposite direction. Next, normal to the plane is in z direction, stress is acting in y direction and opposite tau z by. Okay, these are the components of stress. If you take this is a general state of stress, but what you should know, shear stresses are complementary. This tau xy is equal to tau yx, tau yz is equal to tau zy, tau zx is equal to tau xz. These are complementary. Okay, now as I told you, if I take, there are 9 stress components required uh, to solve the problem. But as I told you, there are infinite number of points, and at each point, the state of stress changes. At each point, the state of stress changes, and also at each point, I can pass infinite number of planes, and at that infinite number of planes, the stresses varies on each plane. But what we discuss for bars and other bars, and we'll discuss for torsion and beams, everything throughout the cross section, anywhere if you take, the stress remains the same. Uniform stress. The stress is uniform throughout the length of the member. It is not varying. Whereas when you take the tapered bar or tapered cross section, deformation varies. Obviously, the stresses and strain varies. Okay, depending, we are taking, even though we are taking the average there. Okay, but when I talk about this, what you should know, when I talk about any body, in a body, there are infinite number of points, and at each point, the state of stress is very different. And also, at each point, I can pass infinite number of planes, and on each plane, and the stresses are different. By knowing the stresses on 3 mutually perpendicular planes, by using transformation, I can find stresses on any other plane. That you should know. Transformation in the sense, by using the given magnitude. In this case, I know the state of stress sigma x, sigma y, sigma z, I know, and by using transformation, I'll find the state of stress on any other. This is the fundamental. Okay. Now coming back to this, tau xy in the sense normal to the plane is in x, normal to the plane is x, and stress is acting in y direction. For example, tau zx is in the sense normal to the plane, normal to the plane is z, stress is acting, stress is acting in x direction. You can see here tau zx. What is that? Tau zx. So tau zx here to be normal to the plane is this, stress is acting in x direction. Okay. Okay. Now coming to your fundamentals is over. Now there is something called as plane stress. What we discussed now is general type of stress. Now we'll discuss plane stress. For example, for example, like a your pressure vessel or a beam, all these are example for plane stress. A bar is an example for typical example for plane stress. Plane stress in the sense there are 9 stress components as we have discussed: sigma x, tau xy, tau xz, sigma y, tau yx, tau yz, tau zx, tau zy, sigma z. There are 9 stress components. When I talk about plane stress, the stresses on one of the plane is negligible or zero, called as plane stress problem. The stresses in one of the plane stress problem. For example, if I consider a plate like this, if I consider a plate, and it is a hole, and there is a hole at the center. It is subjected to load sigma x in x direction, sigma x in this direction, sigma y in this direction, sigma y in this direction. Okay, assume that is of thickness, some thickness. This is z direction, depth is z direction. Okay. Okay. See, in this type of problem, my stresses are only varying in plane, that is x and y plane only, that is x and y plane only. The stresses are not varying, the stresses are independent of z direction. The stresses are independent of z direction, that is all my z components are zero. Sigma z, which is equal to tau yz, which is equal to tau zx, which is equal to tau yz, tau zx, tau zy, which is equal to, I also left out, I'll write tau xz, tau, okay. Sigma x is equal to tau xz, which is equal to tau yz, which is equal to tau zx, which is equal to tau zy, which is equal to sigma z is equal to 0. If I cancel it out here, my tau xz, now tau yz, tau zx, tau zy, sigma z vanishes. I will be left out with only sigma x, tau xy, tau yx, and sigma y. This state of stress where only there is normal stress in x direction, normal stress in y direction, and shear stress normal to the plane is in x direction, stress is acting in y direction. There will be opposite for equilibrium, tau xy, and always you should remember that arrows should meet. When once you draw an arrow upwards, there is an arrow meeting here. This is how you should remember. This is normal to the plane is y, stress is acting in x direction. There is arrow like this, the other arrow should meet like this. Normal to the plane is tau by x. This is causing a clockwise movement. This is causing anti-clockwise movement. This is causing clockwise movement. Sum of the forces in x and y direction are 0. So this state of stress, where the stress is independent of one of the direction, is called as plane stress. So we are left with sigma x, tau xy, and sigma y. Also, we should know that tau xy, due to complementary shear stress theory, tau xy is equal to tau yx. So these are the 4 stress components in case of plane stress condition. Have you understood that? I started with the general 3-dimensional body. In 3-dimensional body, I have 9 stress components, whereas in bar, beam, shaft, we'll consider the stresses are uniform throughout. It is not varying with respect to length, but generally stresses varies from point to point and plane to plane. When I talk about the transformation, if I know the stress on 3 mutually perpendicular plane, I can do transformation and find the state of stress at that point on any other plane. Okay, this is known as transformation. So why we require transformation is, I will discuss that. But let us discuss plane stress first. Plane stress in the sense, the stresses are not varying with respect to one of the coordinate. Okay, that is called as plane stress. Okay, why do we require transformation? For example, if I consider a mild steel bar subjected to axial loading like this, P, it will not break into 2 pieces like this. It will not break into 2 pieces like this. Whereas the mild steel bar shears away like this. Ductile material fails by shearing. Ductile material fails by shearing. That is shear stress. It will fail due to shear stress. Okay, this is how the brittle material fails. This is how brittle material will get, if you cut a cucumber into 2 pieces, that's how the brittle material fails. That is cast iron. Whereas ductile material fails by shearing. Okay, due to shear stress. But how can you say, we have to know that whether which stress is maximum, which stress is minimum, which stress is leading to failure. Okay, that all we should know. So in order to know the maximum stress induced in the material, in order to know, I was plane stress, when I discussed, it was a combination of shear stress and normal stresses, sigma x, sigma y, and tau xy. But in order to know the maximum normal stress and maximum shear stress, and on which planes it is acting, we require stress transformation. In the sense, we are changing the stress from one plane to another in order to know on which plane the stresses are maximum or minimum. Okay. Now there are three mutually perpendicular planes. On which if I do the transformation, at that point we'll get 3 mutually perpendicular planes on which normal stress is maximum, on which only normal stress exists, and shear stress is zero, called as principal planes. Principal planes are principal stress. Upon principal plane, principal stress acts. There are 3 mutually perpendicular planes on which only normal stress exists and shear stress is zero. called as principal planes, and stress on these planes called as principal stresses. So what you should know, if I do the transformation like this, if I at a point, I'll consider one point like this point n I will consider. If I do the transformation, there at this point there is a three set of mutually perpendicular planes upon which there is no shear stress. This tau yx and tau xy are zero, but only this sigma x and sigma y are maximum. The maximum values we will discuss later. But these stresses are only normal. It is perpendicular. No, they are not shear stresses. These are the only normal stresses acting on the planes. Those types of planes are called as principal plane, and the stresses acting on those planes are called as principal stress. It can be the maximum value of principal stress is called as maximum principal stress. The minimum value is called as minimum principal stress. Okay, but since we are dealing with 2D only, our z component of stress is zero. We will be getting only two principal stresses, sigma 1 and sigma 2. Sigma 1 is the maximum principal stress. Sigma 2 is the minimum principal stress. Okay. Similarly, when it talk, there can be three mutually perpendicular planes upon which only normal stresses acts. These are the normal stresses. There is sigma 1 and sigma 2. And shear stresses are zero, called as principal plane. There can also be a case, there are 10 minutes. There are three, okay, this is, okay. There are three mutually perpendicular planes, upon which shear stresses are maximum. But the normal stresses are not zero, called as maximum shear stress planes, and the stress is called as maximum shear stress. See, when I talk about principal stress, there can be three mutually perpendicular planes where there is only normal stress and shear stress are zero. But when I talk about tau max, there is a maximum shear stress. There are three mutually perpendicular planes upon which the shear stresses are maximum. When the shear stresses are maximum, it is not compulsory that my normal stresses to be equal to zero. Okay, we will discuss that. When the shear stresses are zero, when the shear stresses are maximum, it is not compulsory for us to say that the normal stresses are zero. The planes upon which the shear stresses are maximum are called as shear plane, and the stresses are called as maximum shear stress. So, in order to identify the planes upon which the shear stresses are maximum, we will indicate those planes by theta p1 and theta p2 from xy axis. At what angle this plane is, so that I can get sigma 1 and I can get sigma 2. Okay, let me discuss. I have to give few more points. Always you should know that when I talk about transformation, I am talking about with respect to x-axis. If this is my plane, there's a plane like this, and this normal is in x direction. There's one more plane I want to find the transformation. This is at an angle. One more plane, this plane is also given by its normal. This is the plane. In 3D, it can be like this. This is a plane which is perpendicular to this. This is the normal. This is the tangential. For this plane, which is at an angle of theta, some theta angle, I want to find the state of stress. Okay, let me write neatly. Will come to know. This is the state of stress in 2D. Sigma x, sigma x, sigma y, sigma y. Normal to the plane is tau xy. As soon as you read that, opposite the plane, you should write this. Arrows should meet. Normal tau yx, tau yx. This is the general state of stress. For a given problem, this is a stress condition. He has given a state of stress for a point. He has taken a plane, he has taken a body. At this point, he has given the state of stress 50 MPa, 60 MPa, minus 30 MPa. Like this, he has given the state of stress. But I want the state of stress at any other plane, say at an angle theta. Theta is equal to some angle 50 degree or 45 degree. So at angle theta, I want the state of stress at this plane, on this plane. This plane can be like this. Okay, how do you find? So this is the plane. I will indicate this plane by its normal like this. Normal and tangential, two axes, normal and tangential. This is theta. For example, I have considered only this thing. This is theta. Anti-clockwise. I will come to the sign convention in the next class. I will indicate this is the plane I'm talking about, which is this is the general state of stress. When I indicate by a diagonal of some line, there is a plane which is at an angle of this degree with respect to x-axis. With respect to x-axis, with respect to say theta is equal to 45. With respect to 45 degree, with respect to x-axis, my normal to this plane. This plane is if I call AB. Normal to this plane AB is at an angle 45 degree with respect to my x-axis. Always this plane is also indicated, ABCD is also indicated its base normal, that is along x-axis. If I want a normal with respect to the AB plane, I have to rotate it by that angle. Okay, we'll come to that. Okay, I will indicate by a normal and tangential. This is theta. Okay, if I write like this is y, this is x. I can draw this normal. I will draw like this, perpendicular to this. This is normal. If this is theta, if this is theta, give me a moment. If this is theta, this is the normal thing. Okay, this is 90. Give me a moment. Theta, xy, theta, which is perpendicular to this. This is normal. This is this. But right now, this is. Give me a moment. This is theta, and this should be. Where is that? Some point I'm missing. Perpendicular to this. Perpendicular. This is theta. Okay, I will come to this. I instantly unable to say. This angle will also be theta. This angle will also be theta. If this is 90 degree, okay, this is 90 degree. Okay, I'll come to this. It will take a moment to recall. This will also be theta. Okay. Now, see, I am always representing. This is my plane AB plane. This is my plane AB. Next class I will discuss this. This is the plane AB plane. I'm defining my AB plane with respect to a normal. That normal is perpendicular to AB plane. Normal in the sense it is perpendicular. Okay, with reference to x-axis. X-axis is normal to ABCD plane. With reference to x-axis, my normal is at an angle theta. Okay, always whatever plane, whatever you will in the examination, you will say that the state of stress for a given body is given by ABCD plane on which the state of stress is like this. You need to find the state of stress on a plane AB, which is at an angle 45 degree with respect to you'll give in the sketch 45 degree. Okay, then with respect to x-axis, the AB plane normal is at an angle 45 degree. Okay, sign convention, other things we'll discuss later. Okay, this is about your basic of your analysis of stress and strain. Analysis in the sense we are finding it on some other planes. That's why the name came like analysis. Nothing special. Okay. Any doubts you have? I have left it 1.5 minutes. Any doubts? This answer I will tell you. This theta, I am unable to recall. Have you understood this? Anybody have idea? Like anybody can think over it? Why is theta? Anybody? Okay. Can we do like this? Okay. If I draw, okay. If I draw, okay, isn't it? If I draw a vertical like this, if I draw a vertical like this angle is also theta, right? This angle is also theta, right? This is the angle. This is the vertical. The same vertical. This will make an angle theta. If I say this is an angle theta, this will be 90 minus theta. This will be 90 minus theta, and this will be theta. 90 minus theta plus theta will be theta. That's how it's simple it is. I forgot that one. If I write this inclination remains the same, whether like this or like this is theta only. If this is theta, this is tangential. This is theta. This should be 90 minus theta, so that the total angle, this angle is 90. If this is 90 minus theta plus theta should be equal to 90 only. So this has to be 9 theta. Okay, that's all that is. Okay. I'll stop at this point. Next class, I'll give the sign convention, and then don't miss the classes. It is a very simple chapter. I'll give the perfect sign convention, and we can solve this problem. 5 problems if I solve is more than sufficient. From next week.